The Tao of Event-Driven Architectures. The literal meaning of Tao in Chinese is the path or the way. And in that sense, today's talk can be seen as a set of guidelines to build mature event-driven architectures. In a more philosophical sense, Tao roughly means the flow of the universe, or some essence that keeps the universe balanced and ordered. And that's the second layer of today's talk. By applying the 10 simple rules covered today, you will find a natural balance and structure in your event-driven architectures. My name is Luc van Donkersgoed, and I'm a lead engineer at PostNL, the Dutch National Postal Service. And we deliver an average of 1.2 million parcels every day. And this is powered by a fully event-driven landscape. So we literally process billions of events every month in AWS. And today's talk is about how we found our happy path in event-driven architectures. And the reason you're here, the reason you want to listen to this story, is that you need guidelines to grow your event-driven architectures. If you don't use guidelines, your landscape will devolve in a chaotic mess. And that's the natural result of how most event-driven architectures organically grow. They start out with a few interconnected services, exchanging data in a way that is locally optimized. One microservice talking to another, then another, one more. And these talk exactly in a way that works for exactly these services. But as you add more services and nodes to your architecture, and you even start to exchange events across entirely different systems and domains, structure is often lost. The event integrations might use different formats, different languages, different types of encoding and compression, and so on. And at some point, serenity and calm are not quite the words you associate with your architecture anymore. In fact, you might find that operational incidents are hard to investigate and understand. You might look up against the task of adding, changing, or removing a service in your landscape. Or you might not even know what the effects of a change are, where a supposedly safe event mutation leads to downstream incidents. Today, I will tell you about 10 simple rules to keep in mind when designing, growing, and refactoring your event-driven architectures. And these rules are divided into 3 groups. First, we will cover event design, followed by communicating and evolving your events. And in the final section, we'll talk about integrating your events in a larger system. And these rules will keep your event-driven architectures well organized and maintainable. And through this, your developers will work with structured, well-manageable events, which allows them to keep their focus on the business problem to solve. So let's start with the first rule. Use JSON for all of your events. And this might sound like an overly opinionated rule, but it forms the foundation of a well-designed, well-predictable, and well-maintainable event-driven architecture, as we'll see in many of the other rules. And when I say use JSON everywhere, I explicitly mean don't use any other language, anywhere. Don't use XML. Don't use YAML. Don't use plain text. Don't use any other language. And to clarify why, let's take a look at a few other options. First, XML. Well, actually, I'm not even going to go there. Don't use XML. We don't live in the 90s anymore. Next, YAML. And this might seem like a valid candidate for some use cases. However, YAML is built for humans. It is not natively supported by almost every language like JSON is, and most importantly, it is not natively parsable by many cloud services. For example, Amazon SQS, SNS, and EventBridge can apply powerful filtering and routing rules on JSON bodies, but not on YAML. And that's also the reason we don't use Avro or Protobuf. Although these are very efficient and powerful formats, they don't integrate well into the native AWS service landscape. And in practice, we found that even at billions of events per month, we don't need the efficiencies of these formats. Even at that scale, JSON works just fine. And then there's plain text, and this one deserves a bit of additional attention. Let's say you have two systems exchanging data. System A detects an object, a parcel, for example, and notifies another system of its weight. It sends a plain text event that says weight 12. Now, System B needs to parse this event, which is a bit cumbersome. And since System B already knows all the context of this event, after all, it is sent by the weight detector system, the two systems might simply agree to drop the keyword. And this is very efficient, right? And this is an example of a locally optimized system. However, the problem lies in its evolvability. What if System A is upgraded and is suddenly also able to detect the width and the height of the object? How are you going to add that to this event? You could do something like this, but this is impossible to understand and maintain over time. What do these values mean? What happens if any one of them is missing? Instead, use JSON. The meaning of the values is immediately clear. The event can be parsed by any system, and the event is evolvable simply by adding additional keys when needed. And even better is to add the unit to the keys, so there can be no ambiguity about the meaning of these values. So we've established that we should use JSON everywhere. And we can further improve on this guideline by applying rule number 2. Use an event envelope. Now, an envelope is something that you wrap around a message. And an event envelope is no different. It is simply a wrapper around your original object. And one envelope format that has seen a lot of success is the metadata data envelope. And in this envelope format, the original message is contained in the data key. And the metadata key allows us to add additional information about the event itself. This might include fields like the date the event was generated, the type of the field or the version of the field, and much more. And by using a standard envelope with predefined metadata keys for all of your events, makes investigating and understanding operational issues significantly easier. Additionally, it allows consumers to apply advanced processing, such as filtering, in a standardized way. The third rule builds upon the metadata envelope, and the rule is to use a unique event ID for every event. If you have one takeaway from today's talk, then let it be this. Have your producers generate unique identifiers and have them add them to the metadata of your event. I cannot stress strongly enough how important this rule is. Because it allows us to, in practice, this is very easy to achieve. So when a producer sends out an event, they generate a unique identifier, for example, a UUID, and they add it to the metadata section of the event. And now we have a reliable and uniform way to track an event through our systems, regardless of the technology used. And we can use this key to build observability traces, to apply the storage first pattern, Jimmy, where are you? And to achieve item potency. And we'll cover these topics later in the talk as well. Now, the fourth rule that helps achieve serenity in your event-driven architectures is to use schemas and contracts. Schemas define the structure of your events, including which fields are mandatory, which fields are optional, what data type they contain, and even the ranges or enumerations of their values. This is an example snippet of a JSON schema. It is the metadata key that we saw earlier, or defines the metadata key that we saw earlier. So let's look at it line by line. The top line indicates that this schema applies to the metadata key in your event. The next line defines that this key will always contain an object. The third part tells us the properties of that object, the keys, and again also the properties of that key. And then the last part specifies that the event version key in this object will always be present. Schemas are used to clearly define what data will be sent by a producer. And this has a number of important benefits. First, the consumer is able to design their systems based on the contract, even before data is being sent. And the producers can evolve their events safely as long as they adhere to the contract. So in other words, producer systems can, as long as they adhere to the contract, they can never break downstream systems. But that brings up an interesting question, because how do you evolve your events safely while adhering to the contract? Because after all, your landscape is never static, and more data and more insights will become available over time. And that requires you to update your events. So how to update and evolve your events in a safe way is answered by the fifth rule. And the fifth rule is to maintain backward compatibility. But there are two parts to this rule. The first part applies to non-breaking changes. And these are mainly additions to your events, such as adding more fields. And this should always be allowed. It generally follows the be conservative in what you send, be liberal in what you accept principle, also known as Postel's law. So if a producer updates an event to include more data, this should never affect downstream consumers. The second part is about breaking changes, and these are the types of changes that will affect a downstream system, such as removing a required field or changing a field type, for example, from a string to an integer. And a producer can never make these changes without involving their downstream consumers. Now, the correct solution to introduce breaking changes is to use event versioning. So let's take a look at an example. Let's say that system A sends out an event and system B consumes that event. They have defined a contract, and of course system B expects that event to match the schema in that contract. Now, when a producer wants to break that contract, they have to introduce an entirely new event called version 2. And then they need to ask their consumer to migrate to that new schema. In other words, to agree to a new contract. And only when all consumers have accepted that new contract and have migrated to the new schema, can the producer choose to no longer send the initial version. Now, following these principles about versioning and backward compatibility are good protections against unforeseen compatibility problems. And as such, they prevent developers from breaking production, which helps if you want to achieve a tranquil state of mind. The sixth rule is to maintain a schema registry. A schema registry offers a good way for producers and consumers to communicate about their events. A schema registry is an online accessible repository that contains an overview of the events available in your system. It allows producers to annotate and describe their events, and it allows consumers to discover which events are available and their histories. The schema registry is an essential component in mature event-driven architectures. It gives developers ease of mind because they can find all documentation about events in a centralized location. But it only works if it's used as a single source of truth. So producers must send out events that match their schemas, or you're guaranteed to be off the happy path real quick. And that brings us to rule number 7, to use an event broker. Because as you're building and evolving your event-driven architectures, you're probably starting out with direct integrations. But as your landscape grows, you'll find that that is impossible to maintain. And additionally, a mesh architecture like that makes the versioning and backwards compatibility and contract topics that we discussed earlier extremely difficult to implement. And a solution to this problem is to use an event broker. So in essence, an event broker allows a landscape with direct integrations like this to evolve to a star-shaped landscape like this. And in this design, the producers are truly decoupled from their consumers, at least in a technical sense. And if a new consumer needs to subscribe to an existing event, they simply subscribe to the event broker. And now you can see how important contracts have become, because producers might no longer even know who consumes their events. And the entire landscape has become dynamic, ever-changing. Now, to make optimal use of an event broker, it should combine functionality with a schema registry, because this will allow consumers to discover which events are available on the event broker. Additionally, the event broker should validate incoming events against their contracts, because this will protect downstream systems against malformed or breaking events. And in a mature event-driven architecture, you should also be able to query the event broker about which consumers are subscribed to which given events. Because this allows producers to discover who their consumers are and allow them to determine whether they can deprecate or delete older event versions. And so we've arrived at rule number 8. Use event supporting APIs. Events generally tell a fact about a given entity. So in the examples on this slide, the entities are a bike, an order, and an invoice. And the events tell that they have been returned, created, and paid. The event will also contain some additional details like the ID of the bike, the location at which it was returned, and maybe the date and the time at which it was returned. And it is up to the producing system to decide how much detail they want to include in the contents of that event. But it will always be a limited set. It will never be every single detail known about the entity. Adding the color of the bike, for example, does not make much sense for a bike returned event. However, some downstream system might want to know the color of the bikes being returned. And they can ask the producer to add that field to the event, but this might break the scope or the design of that event. And also, where does this end? What if a other consumer wants to know the brand of the bike or the age of the bike returned? Adding every field simply because consumers ask for it does not help to achieve serenity in your event-driven architectures. Instead, the producer should send out the data they believe is applicable for the majority of their consumers, and they should include some sort of entity ID. And at the same time, they should host a resource API that allows downstream consumers to request additional details about that entity for the given entity ID. A GraphQL-based API, for example, might be a good fit for this use case. But of course, there's a natural tension between event-driven architectures and resource-based APIs. After all, scaling an event-driven landscape up to millions of consumers hardly takes more compute capacity than a single consumer would. But if all of those millions of consumers start calling back your API for additional details, your producer system might quickly become overloaded. And producers need to be aware of this balance, and they need to evolve their events based on usage patterns. Now, the rule of thumb is to start with the relevant details and the entity ID. And then you monitor your request-based API's usage, and you discover which fields are often requested. Then you evolve your events by adding those fields, and you collaborate with your consumers by having them use that field and reduce the load on your API. And again, GraphQL might be a good fit because it really allows you to monitor the often requested parts of your data model. There are a few exceptions to this rule. For example, expiring data should generally not be included in event. This might include a stock or a balance. Most of the times, consumers are better off requesting the latest state of this value in an API than relying on the contents of your events. And so we're approaching the end of the list. Most of the rules and guidelines that we discussed so far were aimed at the producer side of things. Rule number 9, to use the storage first pattern, Jimmy, again, where are you, is more aimed at the consumer side of things. So when a consumer receives an event, they can do two things. They can either synchronously process the message, which means they receive the message, take some action based on the event, and only report success when that process has succeeded. Or they can process the message asynchronously, which means that they immediately report back that the event was received and take action at their own pace. In a high volume, low latency event-driven architecture, slow consumers can lead to upstream issues. For example, queues might back up, latency might increase, memory buffers might fill up, or a producing system might experience increased concurrency. And to prevent these issues, consumers should immediately accept and acknowledge events as soon as they can. And this can be achieved by immediately storing the events in a queue or a database. And this is called the storage first pattern. Using the storage first pattern has additional benefits. For example, it allows consumers to deduplicate messages that might inadvertently have been sent more than once because of networking issues or scaling issues, or because you use the express workflows that we discussed earlier. And in this scenario, the unique event identifier that we added to the metadata section of our event envelope really comes into play. Because the consumer can use this event this event ID as a unique key. And when it is received a second time, simply choose to drop it immediately. The source first pattern also provides an easy platform to achieve idempotency. So if a user performs an operation multiple times, the receiving system can simply choose to drop and ignore the event when it is received a second time. And so we have arrived at the last rule. And this combines two of my favorite topics, events and observability. So rule number 10 is to trace your events. So let's discuss why tracing is important. In a large, distributed landscape, the landscape itself can become difficult to observe. For example, it's hard to understand which upstream events lead to which downstream events, which consumers are subscribed to given events, what the root causes of operational incidents are, and which systems might introduce latency in your landscape. The solution is to use distributed tracing, which allows downstream systems to continue a trace that started in an upstream system. So let's take a look at what this means in practice. Our example architecture looks like this. On the left, we have system A, which is responsible for finishing a bike rental. When they are done, they send out a bike returned event, which is received by system B. System B sends out an invoice, and again, when they are done, they send out an event, invoice sent. This is then received by system C, which updates the user's credits. Now, if each of these services emit telemetry, then each of their processes can be considered what is called a span. Literally, it's a span of time spent on a specific task. However, without distributed tracing, these spans will be disconnected and simply live as individual sets of data, not as a cohesive whole. We can use the metadata section in our event envelope again to add these connections between these spans. For example, we can use the trace parent key to add the identifiers of the span that emitted the event. And the downstream system can then create their own spans as child spans of this parent span. The result is that you gain deep insight into the relationships and subscriptions in your event-driven landscape, including any unexpected patterns, volumes, or latencies. And of course, the more complex your system becomes, the more benefit you will experience from these insights. Having a waterfall chart like the one on this slide will be an enormous benefit when an operational incident occurs. And again, that helps to achieve peace of mind. And with that, we've covered the 10 rules to achieve serenity in event-driven architecture. So let's quickly recap the 10 points. First, we talked about event design, and we discussed to use JSON, to use an event envelope, and to add a unique event ID to the metadata section of that envelope. The second part was about communicating and evolving your events, and the rules were to use schemas and contracts, to maintain backward compatibility, or to use versioning if you can't, and to use a schema registry. And the final section was about integrating and supporting your events in a larger landscape. We talked about using an event broker, supporting your events with resource APIs, using the storage first pattern, and to trace your events. But all of this is just a set of guidelines. What is the overarching theme? What is the main takeaway of today's talk? It's this: events are always part of a larger, evolving system. And you should always design your events for that system, not for the local service producing those events. I hope that today's talk will help you evolve your event-driven architectures. And remember, follow the path, achieve serenity. Thank you.